So, you know, that homework was intended to be challenging. I picked sort of some of the more grislier examples. But again, that was done on purpose to adequately motivate you and incentivize you to get up to speed on stuff that you should have hopefully learned last term. So I'm hoping that went well. If it was challenging and it forced you to review a bunch of stuff, then that's good. The assignment served its purpose. You will have a new assignment that will be posted within like a couple hours. As soon as I sit down long enough to look at the book, I'll post your assignment 2. That'll be due next Tuesday. We'll be off to the races. Lab starts.
Lab starts today, room 626. So whoever wants to come to that one, come. I've got a list of the people that are coming on Friday. There's going to be more people in this lab, but I have enough kits and everything for all of you, so don't worry.
Yes, you're all getting a lab kit.
Yeah, it's cute. It comes in a little plastic box. It's got resistors and capacitors in there.
Yes.
What if you're not taking the lab? Is the test going to be related to the lab?
No, it'll be separate grade. I mean, here's the thing. The lab reinforces the lecture. It's not new material, but it's applied material. So, I mean, I might test you on a circuit that you learned in lab, but only because we would also be doing that circuit in class. So it probably wouldn't kill you to read the labs anyway, just to make sure that you're up to speed on what we've been doing in lab. So, you know, it's not off limits. But I'm not gonna. It's not like there's gonna be some stuff that's just lab material that you wouldn't know if you didn't go to lab. Okay. So go to lab. You have to do your pre-lab before you go to lab. Don't go to lab without having done the pre-lab and reading the whole lab. You will waste your time in lab. Okay. So we're going to do circuits today with capacitors in them. All right, because that's kind of where we need to head in this direction. So so let me just kind of recap something that we talked about briefly in class on Friday. Okay, so let's say we have let's be crazy. So what's my output voltage? What's my gain? Why are you not all shouting at me? Seriously, we did this last semester, we did this on Friday. What's my gain? Thank you. Gain is minus R2 over R1, which in this case is minus 5/2. The end, yes.
I forget what one R2 and R1 is.
R2, R1. Okay, so that's my gain. What does my gain do to my input voltage? Multiplies it. Okay, so what do I get when I multiply those two numbers together? Isn't this fun how I threw a monkey wrench in the work by expressing this as 500 millivolts and everybody's like lost their minds? What's 500 millivolts the same as? Half a volt. So instead of giving me your answer as 2,500 millivolts over 2, okay, that's like nonsense. Okay, look at this and say, hey, 500 millivolts. That is half a volt. Half a volt times negative 5/2. Is that right? I'm asking, is it right? The resistors are K, but it doesn't matter. I mean, you want me to put K's here? They cancel anyway, right? As long as they cancel it. The resistors are K. I was just writing this like this because that's the final gain after they cancel each other out. Okay? Cool. Negative 1 1/4 volts. And now, for the part that was confusing everybody. Now what's my output voltage? Still, my output is negative 1.25 volts. Critical. Okay? This part is important. Okay? This has a name. It's called the load resistor. Here's why we put a load resistor.
Should that be 2.25 divided by 2?
Shh.
Times.
Well, oh, I'm sorry. How about that? Sorry, I apologize. Okay. We took our 0.5 volts, multiplied it by the gain of 5/2, and that gave us a product of V out is equal to that. Okay. Now, here's why I'm running my mouth about the load resistor. Okay. You build a circuit to do something, right? You build a circuit to communicate some voltage or some information to something else. So you might build an amplifier to drive a speaker. Okay? So if this is my amplifier, okay, it's not just enough to say I built an amplifier. Now you got to say I built an amplifier and hooked it up to a speaker. There's your speaker. Right? Or I built a control circuit to control a light. Well, here's your light. So it's sort of pointless to talk about your amplifier unless you talk about it in the context of the thing that you hook it up to. So your load resistor is kind of there as a placeholder. It's like your generic thing that you're hooking your circuit up to. Okay? Now, if you're doing it properly, then your amp won't stop amplifying just because you hooked it up to a speaker. Right? That would be a pretty sucky amplifier if, you know, it made a nice sound wave that was only nice until you hooked it up to a speaker. Then as soon as you hooked it up to the speaker, putting the speaker there made that sound wave get all like small and mushy and not sound good anymore. So of course you want to make a circuit where connecting it up to the output, connecting it up to the speaker doesn't actually change the performance of the circuit. And that's what we have here. Before I connected the resistor, I had that voltage, negative 1 1/4. After I connect up my speaker, I have the same thing. Okay? So what changed in the circuit? If the output voltage didn't change, what changed? Current draw. Okay? The op amp is like a little current source. It can either supply current or it can sink current, right, in order to try to drive the appropriate output voltage. Okay? So it says, oh, you put a big load on. Okay, I need to adjust my output current just by this amount in order to maintain the correct output voltage. Yes?
So if the, like, for the load resistor or somehow was an open circuit or it malfunction, would the amplifier still supply current?
Right. Well, if the load isn't open, I mean that's what we started with, right? There's your open load. Okay, negative 1 1/4 volts. That's it. The only thing, I mean, there are practical limitations, right? So if I put 1K here, it works. If I put 2K, it works. It really doesn't matter. The only limitation is there's a limit to how much current you can reasonably expect to suck out of or draw from this op amp, right? So then you open the spec sheet of the op amp and you say, hey, this op amp can only source 1/2 amp of current, okay? And then the transistors inside it burn up. So when you design your op amp, you do have to take, when you design your circuit, you do have to have some understanding of what the limitations are. Like you can't put like a really teeny resistor here, because if you put a really teeny resistor and this thing was still trying to maintain negative 1 1/4 volts, then there would be all sorts of current flowing through there, and then your op amp would burn up. So as long as you're not trying to draw so much current that your op amp can't handle it, this will work. Okay, but that's more of like a fringe. We're not getting into that now. So there you go. There's your load resistor. So far, so good? Okay. So because everybody understands that, we can have the following conversation.
And I have one.
Yeah.
We have differential of amp because of what reason? Like we have negative.
Do we have what now?
Like differential op amps.
What about?
Why we like need a negative voltage?
I don't know. Sometimes you need negative voltage, right? And if you've got, I mean, many signals are I mean, if If you record a speech signal with a microphone, sometimes it's positive, sometimes it's negative. I mean, it's just voltages are negative sometimes. It's just part of daily life. Okay, so let me draw you this circuit. So far, so good? Any guesses what I'm going to draw in the middle? A capacitor. What the hell are we going to do with this mess? Resistor, capacitor. Now we have a problem, okay? Now the math just got ugly, okay? So, let me summarize what I think you need to know. Yes?
Can I take a little wild guess here? I think that's going to be an oscillator.
Nope. Not a bad guess, but we'll get there. Okay, so here's what I want you to think about when you think about capacitors. Capacitor is like a bucket, okay? And you're filling it with electrons. You can fill the bucket. Well, it's not a great analogy. It doesn't work like 100% of the time. But essentially, it's a storage device. Okay, it stores charge. In fact, if you remember, like I'm sure you've seen this in physics class before, a capacitor is basically like two plates of metal. You don't need to draw this. I mean, this is just for fun. A capacitor is basically two plates of metal that don't touch each other. And essentially, you put a bunch of positive charge on one end and a bunch of negative charge on the other end, and it like holds the charge. Okay? So in that sense, a capacitor is important because it has memory. Right? If I change the voltage across a resistor, I don't have any conception on what the voltage was on that resistor a moment ago. But a capacitor is different. If I put charge on a capacitor and then I try to change the charge on the capacitor, it takes time for those electrons to fill up to either add themselves into the capacitor or take themselves away. It has memory. Okay? So memory is important when we talk about signals that change over time. Right? If we talk about, let's say, a square wave that goes down and up and down and up, right? The capacitor has to fill and then empty and then fill and then empty. So it has some memory of what happened before. And that, in a sense, it becomes very powerful. So let's see if we can use our knowledge, what we used on Friday. Remember, we derived the equation for this circuit. Let's see if we can do the same thing now for this circuit and start to talk about what this capacitor is going to do. And talk about where the memory is built into this and how that's useful. So let's apply the virtual short rule of op amps. Okay, what's going to be the relationship between those two nodes? Same voltage, right? Is this a negative feedback configuration? Yes, it is, right? The output is connected to the negative terminal through feedback. And therefore, I can state that these two voltages will be roughly the same. And if this voltage is 0, this voltage is therefore pretty close to 0. In actuality, it's not exactly 0, but it's pretty darn close, right? Close enough that we're just going to choose not to care that it's, like a few microvolts or something. All right? Cool. So, tell me, friends, how much current is traveling in that direction? Yeah, right? If we remember our rules for writing current across a resistor, we draw current in that direction, so positive terminal, negative terminal. The voltage across this resistor is Vin minus 0, divided by the resistor is R. So the total current flowing to the right is Vin minus 0 over R. Well, that was the easy part. Now what? What am I going to do with that current? Where's all that current going to go? The capacitor. There's no way around it. Can't go into the op amp unless your op amp is destroyed. Okay? Current doesn't go into the op amp. So that's it. It's just got to go through the cap. So let's see, just to be a little bit difficult, let me do this for a second. Let me draw the capacitor current going in this direction so we don't get overwhelmed with minus signs. So we'll call this, let's call that I1 and I2 just for a second. So how can I express the capacitor current? Does anyone remember the current equation for a capacitor? C dV dt? Sound vaguely familiar? Does everybody remember the physics of a capacitor, what the equation is for a capacitor? That relates charge and capacitance and voltage? Ooh, okay, good. Yeah, you're all saying sort of the right stuff. Okay, so if you will, okay, let me draw over here because I've already got my capacitor picture. So the equation, this is just sort of like for your knowledge, okay? A capacitor can store charge. How much charge can a capacitor store? Well, the equation is Q equals CV. Okay, now watch this. Q is charge, which is basically a fancy pants way of saying electrons. Okay? C is the capacitance, and V is the voltage. Now this makes sense, because think about this. Let's say I decide to put some charge on this, here's a capacitor of a certain size, all right? And I put some charge on there, and that gives me a voltage, okay? So that yields a voltage. If I now come and double my charge, how do you think, intuitively, if I double my charge, how do you think that should affect my voltage? You should double it, right? If I put twice as many electrons on this, then that means I've got twice the amount of stuff stored on this capacitor, and therefore I should have twice the voltage. So that's okay. The equation actually pans out, right? This kind of works. Same thing. If I keep my charge the same, but I make the capacitor smaller, what happens to the voltage? Yeah, right. If I keep the charge the same, and I half my capacitance, I therefore double my voltage. Okay, and that makes sense. Because if I half my capacitance, that means, how do I half my capacitance? What's that? Do I make the capacitor bigger or smaller to half the capacitance? I don't remember. Damn, I painted myself into a corner. Let's see. If you make the capacitor bigger, it can store more charge, which means it's going to be a bigger capacitance, I think. So if I, oh, right, yes, I'm good. I'm back now. Right, they add together. That's a great intuition. Thank you. Good. Think of it like, here's how I like to think about it. If I were to, okay, so I'm basically trying to build intuition to convince myself that this equation makes sense. So that's the intellectual exercise I'm having in my own head. And that you should have in your own head too, because nothing sucks more than having an equation that you don't really understand, right? So take the equation, probe it, make sure it makes sense, then we're cool with it. So we think this is the equation. We said, does it make sense that if you half the charge, you half the voltage? I think that's okay. Now I'm asking the question, if you hold the charge constant and halve the capacitance, the equation predicts that you double the voltage. And I'm asking, does that make sense? And it does. Because if you have the capacitance, that means you're going to make the capacitor smaller, like half as big. So now what I'm saying is, if you take the same charge, but you mush it into a smaller capacitor, that's actually like a bigger density of stuff, right? You've packed more electrons into a smaller space. So you've actually had to do more work to do that. And therefore, there's more voltage across the capacitor, right? If I had, just in this dumb example, right? If my capacitor was, let's say, this big, okay, and I put 4 electrons across it, okay, now I'm essentially saying, let's take those same 4 electrons, but put them on a capacitor that's half as big. So now, wow, now I really had to work hard to pack those 4 electrons on there, right? That took a lot more work to mush those 4 electrons onto a smaller space. So can you feel that there's more energy stored in this capacitor? Because you had to work harder you had to like mush them in there because there was less space to put them. So good, there's more energy in this capacitor. Therefore, there's more voltage across it now. And that's exactly what this equation predicts. If you hold the charge constant and you have the capacitance, you've doubled the voltage. So I like this equation. This equation makes sense to me. Now, I'm going to differentiate both sides. Okay? So watch this. If I differentiate both sides, I get dq dt, so the change of charge with respect to time, equals, what am I going to do with the capacitor? Can you differentiate a capacitor? It's just a constant. That's just a physical property of the capacitor. So that doesn't change anything. And then I'll just differentiate the voltage, dV dt. And what is dq dt? What is the change of charge with respect to time? That is the definition of current. If you take electrons and you frog march them across a wire, if you move electrons, that's the definition of current. And that's what this is. Change in charge with respect to time, that's current. So this whole little aside that we've done here is I said, what's the current equation for a capacitor? And y'all just said, oh, yeah, there's a derivative. I don't, okay. So I'm coming back to you and I'm saying, look, this stuff's not magic, okay? We started with a physical equation, which we've tested at an intuitive level to make sure it makes sense. We've differentiated it, and now we've gotten an equation. So this equation is not magic. It follows from the physics of what's a capacitor. Now, we don't have to derive it every time, and this is just so you know that we didn't build this out of, out of fantasy land. So in our case, the current across the capacitor is going to equal C dV dt. What's the V that's involved? What's the voltage across the capacitor? What's the V that I have to worry about? What's the voltage across my capacitor? Is it V in? Oh, it's V out. Yeah. Perfect. Okay. Because on this end it's V out, and on this end it's 0. So it's because we gotta make sure we do this properly. It's d V out dt. Yeah. And what's the relationship between I1 and I2? What's that? You said it. They have to add to 0, right? If I've got 1 amp going in this direction, I better have -1 amp coming in that direction, right? The way I've drawn it, they have to add to 0. So by definition of Kirchhoff's, current law? Is that what they still call it? All right. I1 plus I2 have to sum to 0. So let's make it happen, friends. I've got V in over R, right? I can ditch the -0, because that doesn't really add anything to the conversation, plus C dV out dt equals 0. Right, so my whole job is I'm trying to solve for V out as a function of all the other stuff. Okay, so what do I need to do to get V out? Yeah, well, first I need to get all the others, I need to get everything, I need to try to isolate dV out, and then let's see what happens next. So from this step, I'm going to move everything over to the left. I'll move the V in term over to the right, and I'll divide through by C. So if I do that, I'll be left with dV out dt. Did you know this is all in your book? Equals minus V in over what? RC. Okay. Good. I'm liking it. And what's the final step for isolating V out? Multiply by dt. Okay, fine. dV out equals minus V in over RC dt. Help a guy out. I want to get V out. I've got the derivative of V out. Integrate. Okay, well this ain't too bad. If you derivative, if you integrate dV out, you just get V out. That part was easy. All right, what am I doing with the thing on the left? Right, the 1 over RC is a constant, so that comes out, minus 1 over RC. Just add a T? If V, but that only works if V in is a constant, right? Right? If V in was a constant, then yeah, then it would be V in times T. But what if V in wasn't a constant? Right? What if your V in was a, what if your V in looked like this? At this point, the best you can do is say integral of V in dt. The end. So, what is this circuit? What does this circuit do to your input? Yes? A damper? Close. I wouldn't call it a damper, but you're kind of on the right track. Don't overthink it. It's an integrator, right? It just takes your input and integrates it. Isn't that cool? We've built, write it right next to the circuit, an integrator. So let's say that you're building a car, okay, like a remote control car, and for whatever reason, you've got some sensor that outputs an analog voltage that corresponds to velocity. Okay, so here's your car. Did you know I can't draw? Okay, it's actually better than average. The only thing that was bad about that car is as I was drawing it, I thought it was going to drive to the right. But it clearly looks like it's going to drive to the left. But it does look like a car. I have little kids. I can draw hippos. I can draw giraffes. I can draw cows. I do a lot of like animal drawings at home, but I don't draw a lot of cars. Okay. Okay. So your car, you've built it, and it's got some sensor. It's got a sensor in there connected to the wheels or something that tells you the velocity. Okay? Which is cool and all, but I want to know where I am. I don't want to know my velocity. I want to know my position. I want my car to be able to let me know where I am on the map, right? Because I've got a map, right? And I've got GPS. No, I don't have GPS. Right? This is the days before GPS, so that's why this example sucks, because we all have GPS now. Okay? But let's say, according to my map, I know I need to make a left-hand turn after half a mile. Okay? So I need the car to, I need to be told when I've traveled a half a mile. Okay? And I've got a velocity sensor. What do I need to do to my velocity signal in order to get position? Integrate it, right? Don't we know that when you integrate velocity, you get position? They still teach physics, right? At this school, maybe? Okay, good. How am I going to integrate this analog velocity signal? With an integrator. Okay? You take your velocity signal. You know, you have to do a little thinking about what you want for your resistor and capacitor value. But you integrate it, and now you know position. It's a pretty handy circuit to have. Wouldn't you agree? Yes.
So what would you make the resistor capacitor or something like that?
Well, really, you can make them whatever you want within reason. That's sort of true. It basically winds up being like a gain factor. You could probably, It's not that critical, I would say, for this example. You could, as long as you knew what it was, you could account for it. It's pretty neat, right? So let's try an example. Let's actually try this. So let's say, no, I guess I don't want to erase the circuit. Let's see. Let's work over here. Yes.
Comparing to the last one you drew with the last op amp,
Yes.
why you said the voltage was going to be 0 over here?
Yep. Over here.
Yeah.
Yeah.
But the last one we said the voltage was going to be. We said there was a voltage and a current.
Are you talking about this circuit?
Yeah.
Is that one?
No. Today's the other one with the half millivolt.
Yeah. Well, there's a half millivolt was here,
Yeah.
but not here.
Okay.
Right. That voltage was 0 in that example as well. Cool. So let's say let's let R equal a kilo ohm, C equal a microfarad, and let's let your voltage. Oops. Let's let that do that. Let's put some numbers on here. Oh, rats. Now I got to do this math in my head. Hold on. Time constant is a millisecond. If I integrate millisecond. Sorry, I'm just having a little moment here.
It's microfarad, right?
That is a microfarad. I think this example will work nicely. Let's see, 1,000. Oh, who cares? Okay. Let's say that's 1 millisecond, 2 milliseconds, 3 milliseconds, and that's 1 volt, and that's minus 1 volt. So we've made ourselves a square wave. Square waves happen from time to time in engineering. So what do you think is going to happen? What do you get when you integrate a square? Area. Thank you. What do you get when you from time 0 to time 1 millisecond? This is a constant. What do you get when you integrate a constant? Nothing. Okay. Anyone else? A line. What kind of line? Straight line. Thank you. That's killing me. Straight line. Yeah, you get a straight line. Yeah. I mean, in general, we know if you integrate a constant, you get a line, right? If you integrate a negative constant, you get a negative line with a negative slope. Okay? And if this line is sort of equal and opposite to this line, then when you're done integrating all the way from 0 to 2 milliseconds, what should you be back at? You should be back at 0, right? Because this area under the curve is equal and opposite to this area under the curve. So by the time you've integrated your way over to 2 milliseconds, you should get 0. So I mean, just by eyeballing this, I should be expecting that the integral of this square wave is going to kind of look like that. Okay, but let's put some math on here and at least see if we can label the axes reasonably well. So according to the math that we did, we expect that V out will equal minus 1 over RC. Okay, what is 1 over RC in this case? What is RC? Oh, no, a number. I want a number, please. Okay. Close. Watch this. Seriously, this is engineering 101. K is 10 to the 3. Micro is 10 to the negative 6. So if you multiply 10 to the 3 times 10 to the minus 6, you get 10 to the negative 3. You add the exponents. 3 minus 6 is minus 3. So the product of those is 1 times 10 to the minus 3. Okay, so in this case, you have RC equals 1 E minus 3, which is a fancy way of saying 1 millisecond. Now, I didn't want, where am I? I'm lost. I don't want RC, I want 1 over RC. So, if RC is 1 times 10 to the minus 3, 1 over RC had better be, exactly, 1 over RC had better be 1e to the positive 3, or 1,000. Right? I'm just saying, you don't always have to grab the calculator. Okay, so in this case, and not just because it's like a cool party trick, but it's handy to be able to just sort of see these relationships as you work through these problems. Okay, so minus 1,000 times the integral of v n of t. And in the first 1 millisecond, v n of t equals what? Equals a constant of 1 volt. Cool. So when we integrate 1 volt, we're going to get, when we integrate 1, we're going to get t. Okay, so minus 1,000 t is what I'm going to get for the first millisecond, because I just integrated the value of 1 for v, and by that value of 1 only applied for this stretch of time. Okay, so I was almost right. I got the only thing I was wrong was about, when I drew this picture, I wasn't taking into account the fact that my integral had a minus sign in it. So if I go to, so let's plot that 1,000t, sorry, that minus 1,000t. Okay, so plot my output voltage, t, 1 millisecond. So we've just looked at this, and we've decided in the first millisecond I'm going to get negative 1,000t. So the equation of this line is negative 1,000t. What's that voltage going to be? Absolutely, negative 1. I mean, it's plug and chug. This is the equation of the line. This is the time that I want to know what this voltage is. So if I take 1,000 times a millisecond, this is 10 to the 3. This is 10 to the negative 3. You multiply them, you get 10 to the 0, which is 1. Negative 1 volt. Okay, that's a start. Let's do this part of the square wave now. So when I do that part of the square wave, what's going to change? Does the minus 1,000 change? The minus 1 over RC? No. So I've still got minus 1,000 times the integral of, what's my V in? Now we're done with this region, right? We finished this. Now I'm over here in this region. So what's an expression for my input voltage in that region? Yeah, it's just the constant. Negative 1. So what's that going to leave me with? Thousand T. That's another line. Here's a question. If I go to plot 1,000t, let's see. Well, if I plotted 1,000t, wouldn't that look like this? Isn't that the plot of 1,000t? I mean, this is the plot. I'm not lying. This is the plot of 1000T. Is that right? That's what I should draw? That's what's going to happen in this circuit? Oh, wait, it's got to connect to this endpoint? We're going to talk about memory now. Okay? So look what's going to happen. This is the plot of 1000T. It's true. But it really doesn't make any sense. If I drew it like this, essentially what you would be saying is that you got down to -1 volt, and then at t equals 1 millisecond, you instantly jumped up to here, to 1 volt? Is that possible? No. Right? That would require an instantaneous bunch of charge to go on your capacitor, which doesn't make any sense, right? Your capacitor cannot instantaneously take on a whole bunch of charge. So here's how we're going to fix this problem. There's something we've left off our integral. Elliot knows what it is, but he's the TA, so. Not time. You get the constant, right? There's a constant of integration that goes at the end. And what does a constant of integration do to your line, like graphically? Well, if you add a constant, right, it moves it up or down depending what the constant is. So guess what? Let's save ourselves a bunch of trouble and assume that here's your 1000T, and if I add the correct constant to it in order to make this math work out, it will be enough to bring that line down so that you get that. You still got your 1000T, but now you're adding an initial condition that says your voltage can't change instantaneously. Okay? You still got your 1000T, it's just 1000T plus an initial condition that makes this work out so that you don't have an instantaneous change on the cap. Because the cap has memory, right? The cap, you can't just tell the cap, no. You're just going to instantaneously lose a whole bunch of charge. It doesn't work. Yes? I'm sorry? We're plotting here. This is the plot of V out. This is the plot of V in. This is V in. Okay? So was I right? After 2 milliseconds, did we get back to 0? Absolutely. Okay, and then it's wash, rinse, repeat, right? Down, up, down, up. Now I could put in a lot more sophisticated, we've just done a square wave. I could put in a triangle wave and integrate that. I could put in a cosine and integrate that.
So we know when we have discovered the output can be like triangle wave.
What's that?
When we have a square wave, we have
You're always going to get a triangle wave for this particular circuit. Pretty nutty, right? Maybe.
And we know that triangle wave is down because we had the negative.
Exactly. There was a negative that came along. Because it's an inverting op amp. We had that same negative when we just had resistors, right? It was minus R2 over R1. It's the same thing. You still have that resistor there. Okay. So we've got about 7 minutes left. I think what we're going to do is we're going to finish with this circuit. But I'm going to ask you, we're going to, instead of putting in a square wave, we're going to put in a cosine. And we're going to ask ourselves an interesting question, which is, what happens at different frequencies of cosines as you put them through this? And I want you to remember what we're going to talk about, because in about a month, this is all going to become really, really relevant. Okay? You ever heard of a filter? High-pass filters, low-pass filters. Is that a term that you've at least heard? Who knows what somebody explain to me in like one sentence of non-jargon, like what's a filter? Yeah. Sorry, go ahead.
If you want only like a high frequency, it only allows that to pass. Or if you only want a low, it allows that to pass.
There you go. So we think of signals as having high frequencies or low frequencies. Like if you've got an audio signal, you could have bass, you could have treble. Right? Now if you want to build a speaker system where, let's say you've got a tweeter and you only want the high frequency portion of your signal to go to the tweeter, what you might want to do is to build a filter. That filter would pass the high frequency portions of your audio signal. It would therefore be a high frequency filter, a high pass filter, and you would take those high frequency signals and route them to your tweeter. Guess what kind of filter you'd build for your bass, for your woofer? Low pass, right? You take the low frequency portion of your signal, okay? So therefore you build a low pass filter that takes your whole signal, it just passes the low frequencies, and it routes those to your woofer. Okay, that's how you build those. That's like what a filter is. So let's stick with I'm going to keep the circuit equation over there. And let's actually stick with the values of R and C that I have. So let's let x of t equal cosine of 2 pi 100 t. What's the frequency of this signal? Does anybody remember how to do this? What's the frequency of this cosine? Yep. It's always 2 pi times the frequency in hertz. So this is a 100 hertz cosine. It repeats 100 times a second. So let's find out what happens when we take this cosine and pass it through our circuit. Okay, the circuit that I've now erased, right? The resistor and then the capacitor and the feedback loop. So the output, V out of t, is going to be minus 1 over RC. So what's minus 1 over RC in this case? I'm going to stick with the same resistor and cap value. It's still negative 1,000. That hasn't changed. Negative 1,000. And now we need to integrate V in. So what is the integral of my input voltage? How do we integrate cosines? Sine. Okay, well, let's get some scratch paper going over here. Integral of cosine of omega t dt equals, no, it's sine of omega t times what now? Is it omega or 1 over omega? It's 1 over omega. Right? Because look, if you take the derivative of sine, you get cosine omega t, and then the chain rule brings the omega out. That cancels with that, and you get your cosine back. So this is definitely right. You with me? Now watch this. So it's 1 over RC times the integral of my cosine. And according to this baloney that we just wrote over here, this identity, this should come out to 1 over my frequency. So it should be 1 over 2 pi 100 times sine of 2 pi 100 t. Are you with me? Okay. So, this is interesting. I started with a cosine of amplitude 1. And now for my output, I get a sine wave. Well, a sine wave is just like a cosine with some phase shift. I'm not going to lose a whole lot of sleep over that. But what happened to the amplitude? I had an amplitude of 1. Now I have an amplitude of it's 1,000 divided by 2 times pi times 10. So let's see if we can do this without too much work. 1,000 divided by 100 is 10. 10 over 2 pi. So it's, well, okay, let's see. 10 over 2 pi is basically 6. So like what? 1.4? Is that roughly right? Good enough for government work. Okay. So this is basically like minus 1.4-ish times sine of 2 pi 100 t. So, to summarize, I took a kind of a low frequency signal, and roughly speaking, that's what I got out. Now, guess what we're going to put in next? A high frequency signal. Yes, you guessed right. Okay, so let's try this again. Let's let x of t equal, oh, I've got 3 minutes left. We've got all sorts of time. Cosine of 2 pi 10,000 t. So this is a 10,000 hertz signal. So, low frequency, high frequency. Let's do the math again. What's my V out? Well, according to my equation, it's still minus 1 over RC times the integral of my input. And we've agreed that the integral of my input is 1 over omega times sine of 2 pi 10,000 t. Okay, so I started with a cosine whose amplitude of 1. And my output is now a cosine with or a sine with an amplitude of, let's see, 1,000 over 10,000 is 0.1. 1 over 10, that's 0.1. 1 over 2 pi is like 1 over 6. Let's see, so 1 over 6 is like, it's half of a third. A third is 0.33. Half of that is like roughly 0.15. And I want a tenth of that. So it's like instead of 0.15, it's like 0.015. So this is like roughly minus 0.015 sine of. Okay. So into this filter, I put in a low frequency signal and I put in a high frequency signal. Which one got passed? The low frequency signal or the high frequency signal? Here I put in, don't worry about the minus sign. The minus sign is like a phase shift for a sinusoid. So don't dwell on the minus sign. So in the low frequency case, I started with a 1 volt signal. I got out a 1.4 volt signal. Does that sound like it was being passed or being rejected? Passed. Now over here, I put in a 1 volt signal. What'd I get out? Not much. Not much at all. So what got passed? Low or high? Low frequency. What got rejected? Low or high? Did I build a low pass filter or a high pass filter? I built a low pass filter. It goes to your woofer. Okay? So this is like the whole point of this semester, okay? Is eventually we're going to get very good at taking AC signals, sine waves and cosines, and sticking them into circuits and making intelligent guesses about what comes out the other end. Okay? That's why we did this example. Not because I need you to know this right now or anything, but just to motivate the case that I'm going to make for you this semester. We're going to build circuits, we're going to stick in cosines, we're going to make guesses as to what comes out the other end. Okay? And we're going to do that because the ultimate goal is to build filters. All right, have fun in lab today.